Hi again, this is the fourth in a series of 5 videos on row reduction, and in this video we are going to solve our first system, and we will discuss guidelines that will help you know exactly what to do at each stage of the process. Since the first video, we've actually been working with the same system of equations, which is written here. But in this video, we are going to use what we've learned to solve this system from the very beginning. And remember that the first step is to form what's called the augmented matrix. And the way that we do that is we just go back to the system of equations and make sure that each equation has the variables listed in order, x, y, z, which they do, and then we put the numbers into the matrix in the same order. So in the first equation we have 3, 6, 12, and 9, and that becomes the first row in our matrix. And then we do the same for the other equations. So let's see how that looks. Great. The first row is just what we said it would be, 3, 6, 12, and 9. And the second row is filled out similarly. And the third row has something a little bit different because the third equation is missing an x term. And the way that we deal with that is we just remember that 0 times x is 0, and adding that doesn't change the equation. So we fill that missing entry in with a 0. Next, let's go ahead and reduce this matrix. Okay, so we actually did the first few steps in a previous video, but at that point we were just learning how the operations worked. Now we're going to understand why we would want to use each operation. The idea is that starting with the augmented matrix here, we will apply a sequence of row operations until we get a matrix that is in reduced form. And since this process requires a lot of steps, it's helpful to have some guidelines that will tell us what we should do at each stage of the process. Right now what we'll do is we'll just state each guideline as a goal so we understand what we're trying to do, and then next we'll talk about how to accomplish each goal in detail. The first goal then is to create a leading one in the first row. And so you can see that means turning this 3 into a 1 in our example. The next goal will be to clear the leading one's column. In other words, we want to make all the entries in this column besides the leading one a 0. Specifically, we'll need to turn this 2 into a 0 in the next matrix. And then after that, we essentially repeat the process. So we'll create a leading one in the second row, and then we'll clear that leading one's column. Let's see how to accomplish our first goal of creating a leading one in the first row. Essentially, we're going to always do this in the same way. There's one exception, but we'll talk about that later. So basically, we're always going to multiply by the reciprocal of the leading non-zero entry. In our example, the leading non-zero entry in row 1 is 3, and the reciprocal of 3 is 1/3. Remember that in general, the reciprocal of a number is just 1 divided by that number. So if you have 5, for example, the reciprocal would be 1/5. Going back to our example, we're taking row 1 and multiplying by 1/3. The first entry we'll get is 3 times 1/3, which is 1, just like we wanted. And the next entry is 6 times 1/3, which is 2. And then 12 times 1/3, which is 4. And 9 times 1/3, which is 3. Before we move on, I want to make it clear why we always want to create a leading one in the same way. And let's do this with an example. So, something that often happens is that a student will be reducing a matrix and everything will be going along nicely. In this case, say we're at a step where we've already created a leading one and we've cleared the first column, and we know that the next step is to get a leading one in the second row. Well, you might observe that we have a 4 above the 5, and that's just 1 unit away from 5. So you might think, and this is not completely unreasonable, that you could just take row 1, multiply it by -1, and add it to row 2. And that will give us a 1, a leading 1 in the second row. Let's see how that works. Remember that when we use this operation, we just change the row to which we add, because we're just trying to get a 1 here. So we'll go ahead and copy down the rows that don't change first. And then what do we get in the second row? One way to help us keep track of everything is to first write down the result of row 1 times -1 above the matrix. So that would be -1, -4, 0, -3. And then we'll add that to row 2. So we have -1 plus 0 is -1. And the next entry is -4 plus 5, and that's the positive 1 that we were hoping for. And then we have 0 plus 1, that's 1, and -3 plus 2, which is -1. Okay, but what went wrong? Well, we did get our leading 1, but we undid all of our work in clearing out that first column. Now we have a -1 where we want to have a 0. So to avoid this type of situation, we're just going to stick to our guidelines, which tell us exactly what to do, essentially, at each stage of the process. Next, let's see how to accomplish the second goal, which is to clear the leading one's column. Again, we are always going to do this in a very specific way, and there are no exceptions. We will always just multiply by the opposite of the entry we're trying to clear, and then add. In our example, the entry we want to clear is the 2 below the leading one, and the opposite of 2 is -2. The idea is that the 1 is essentially your friend, because in order to make this 2 a 0, I want to multiply row 1 by something so that I get a -2 in the first entry, and then when I'll add that to the 2, I'll get 0. And 1 is just really easy to work with. I don't have to think very hard about what should I multiply 1 by to get negative 2. Well, I just multiply by negative 2. So let's see how this works. We're going to take row 1, multiply it by negative 2, and then add it to row 2. Again, if we like, we can write the result of multiplying row 1 by negative 2 above the matrix. So in that case, we would have negative 2, negative 4, negative 8, and negative 6. And then we will just add the corresponding entries to get the first entry. So we'll have this 2 plus negative 2. That gives us a 0 here. And then 4 plus negative 4. That gives us another 0. And negative 8 plus negative 4. That's a negative 12. And then negative 6 plus 6, which is 0. Let's see if the slides show us the same result. And they do. Now, what we've done so far is we've accomplished the first goal, which is to get a leading 1 in the first row, and the second goal, which is to clear the column of that leading 1. And then remember, the next goal is to get a leading 1 in the second row. Let's see how to do that. Here we encounter the exception that I mentioned before. So our leading non-zero entry in the second row is negative 12, and one way to make this a 1 would be to multiply row 2 by the reciprocal of negative 12, which is negative 1/12. However, once we turn that negative 12 into a 1, we can see that our leading 1s will not form a staircase. And so if we anticipate that, we have another option for creating the leading 1, which is to interchange 2 rows. In this case, we want to interchange row 2 and row 3. In other words, we take row 2, move it down to the third position, and take row 3 and move it up to the second position. And now we have a leading 1 in the second row like we wanted. Given our new understanding of the guidelines, we can go ahead and complete the reduction. We have our leading 1 in the second row, and the next step would be to clear its column. So we need to make this 2 a 0. And how do we do that? Well, we want to multiply row 2 by the opposite of the entry we're trying to clear, which is negative 2, and then add that to row 1. And remember, it's helpful to just copy down the 2 rows that don't change first. Since we're trying to make this 2 a 0, it's the other rows that don't change. And what do we get in the first row? Well, when we multiply row 2 by negative 2, that gives us 0, negative 2, negative 8, negative 14. And then we're going to add to row 1. 0 plus 1 is 1. Negative 2 plus 2 is 0. Negative 8 plus 4 is negative 4, and negative 14 plus 3 is negative 11. What's next? Well, we cleared the column of the second leading one, and so next we want to get a leading one in the third row, which would have to be here. And we will do that in the normal way, which is to multiply row 3 by the reciprocal of the entry we'd like to be a 1. That's negative 1/12. We'll just copy down the entries that don't change. And what do we get in the third row? Well, multiplying by negative 1/12 will not change the entries that are 0, and so the only entry that changes is the negative 12, which will become a 1. Next, well, we have our leading 1 in the third row, and we'd like to clear its column. A quick tip about this: normally it's not the best idea to combine two row operations in the same step. It can cause confusion or mistakes, but when you're using a leading 1 to clear its column, when you're at that stage of the process, then it's safe to perform more than one operation per step. In particular, here we want to clear 4 and negative 4, and we'll do both of those in the same matrix over here. So let's clear we can clear either entry first. Let's start with the 4, and to do that we use the same row operation as always. We just multiply, we use the 1. The 1 is our friend, so we want to multiply row 3 by the opposite of 4, which is negative 4, and then add that to row 2. First, we will copy down the row that doesn't change, and since we're clearing the 4 and the negative 4, the row that doesn't change is row 3. Now we can apply our row operation. So multiplying row 3 by negative 4 gives us 0, 0, negative 4, 0. And then we want to add that to row 2. And what do we get? Well, 0 plus 0 is 0. 0 plus 1 is 1. Negative 4 plus 4 is 0. And 0 plus 7 is 7. How about the next operation? Well, we said we want to clear the negative 4, and to do that, we will use the leading 1. Specifically, we will multiply the leading 1's row, row 3, by the opposite of negative 4, which is positive 4, and then add that to row 1. What do we get? Multiplying row 3 by 4 gives us 0, 0, 4, 0. And this time we are adding to row 1. And we have 0 plus 1 is 1. 0 plus 0 is 0. 4 plus negative 4 is 0. And 0 plus negative 11 is negative 11. Okay, that completes the row reduction. And the next step is to convert our reduced matrix back to a system of equations. The first row then represents 1 times x plus 0 times y plus 0 times z equals negative 11, and that's the same as just x equals negative 11, which we have here. Similarly, the second equation would just be y equals 7, and the third is z equals 0. So this is one way to write our solution. We found the numbers that solve the original system. X is negative 11, y is 7, and z is 0. We can also write the solution, if we want, as an ordered list of numbers. This is called an ordered triple because there are 3 of them. And that's just another option. Alright, we've solved our first system. And to be safe, let's check our answer. We can do this by plugging it into each equation in the original system that we started with at the very beginning of this video. Specifically, we want to take the value for x, of course, and plug it into where the x is in the equation, and take the 7, plug that in for y, and so forth. And this is what we get here. What we're looking for is whether or not the left-hand side is actually equal to the right-hand side. Let's see. So 3 times negative 11, that's negative 33, plus 6 times 7 is 42, plus 12 times 0 is 0, and negative 33 plus 42 is positive 9. We can check each of the other equations in the same way, and they should all be true. If even one of these equations is false, so for example, if we get something like 3 on the left and 5 on the right, which is telling us 3 is equal to 5, that just means that the answer we got, which we thought was a solution, is not actually a solution. Now that we understand the guidelines, we can describe them each in more detail than we did at the beginning of the video. So they say, to start off, we want to begin with the first row, and what do we do to it? We want to create a leading one, and then which operations do we want to use to create a leading one? Or is it always the same operation? Well, almost always we want to multiply by the reciprocal. But sometimes, remember, if we need to create a staircase, then we'll need to interchange rows. Okay, once we create our leading one, what happens after that? We want to clear its column. And which operation or operations should we use to do that? Always the same. You want to multiply by the opposite of the entry you're trying to clear, and then add. Okay, once we've completed these 2 steps, get a leading one and clear its column, what do we do next? We just move on to the second row. We get a leading one there and clear its column. Then what? We just repeat with each row until we can't do it anymore. Okay, and you might be wondering, well, it seems like at each stage I know almost exactly what to do, but is it possible that I'll have maybe 2 options at one particular step? That is possible. So 2 people could apply these guidelines and not use the exact same sequence of row operations. However, they will always get the same reduced matrix at the end. That's one of the advantages of the definition of reduced matrix that we use. There's only one reduced form for any given augmented matrix. Okay, we mentioned at the end of the previous video that there is an easier way to decide when a matrix is reduced. Before, we just checked each of the 4 conditions in the definition of a reduced matrix. Now we're ready for another approach that takes a bit less effort. So instead of checking each of the 4 required conditions, you can attempt to reduce the matrix according to our guidelines. And if there's nothing to do, then the matrix is already reduced. And if there is something to do, then it's not reduced. So let's take a quiz just to practice this. Is the first matrix reduced? Well, let's see. We would want to get a leading 1 in the first row. That's done for us. Then we would want to clear its column. That's done for us. Then we move to the second row. We want to get a leading 1. That's already done. We'd want to clear its column. That's already done. Next step, we move to the third row. We want to get a leading 1. That's already done. We want to clear its column. That is not done. There's a 2 above this leading 1. And so there's still work left to do. If we were going to reduce this matrix, we would have to turn that 2 into a 0. So this matrix is not reduced. Just so you can see how quick this can really be, let's go ahead and run through this next matrix a bit faster. So we have our leading 1 in the first row, and its column's clear, our leading 1 in the second row, and its column's clear, and our leading 1 in the third row, and its column's clear. And we have this nice staircase. So yes, there's no work left to do. This matrix is reduced. How about the next one? We have our leading 1 in the first row, and its column is clear, our leading 1 in the second row, and its column is clear, and our leading 1 in the third row, and its column is clear. But in this case, hopefully it will stand out to you that we don't have a staircase, and so we would need to switch the second row with the third. So this matrix is not reduced. That's it for this video, and in the next we will talk about whether a system can have no solution at all or more than one solution, and in that case, how to find all the solutions. Thanks again for watching, and I'll see you soon.